from the third law that we create the basis for absolute entropy. And we've already talked about this a little bit, how when we change phases or we change chemical structure, that can change entropy. Well, that scale, like I said, is relative to the third law. And if we think about that for a moment, okay, we wrote entropy as S equals K natural log of W. And so if we think further on this third law, okay, that tells us that S has to equal 0 at 0 Kelvin, right? Well, if S is equal to 0, then that means W has to equal 1. So in other words, at 0 Kelvin, there is only one singular way to arrange any molecule, okay? As we then increase the temperature of our molecules to some standard state, so for example, standard state of a solid would be given at a pressure of 1 bar and the most stable allotrope of that element. For a liquid, similarly, for a gas, similarly, and for a solution, standard state is 1 molar. So as we build up from the third law, so from 0 Kelvin up to these standard states, we then get our standard molar entropy, which is given in this table here. And of course, we can now use this table to calculate number of microstates, which gives us a metric for entropy. So for example, if we look at carbon diamond or carbon graphite, those are very low, 2.4 for diamond and 5.7 for graphite. And this is at room temperature, okay? So these values are at 298 K. So what I find amazing about that, if we were to actually calculate the number of microstates for diamond and graphite, so let's see, I did it for graphite. So at 5.7, we get W to equal 1.98. So basically call that 2. So that's pretty incredible. So that indicates graphite, even at room temperature, is a very low entropy material. So it is a very orderly, regular material. But if we were to look at something like sucrose with 360.2 joule per mole per K, if you calculate the number of microstates of this material, it's something like 6.5 times 10 to the 18, which is just crazy. So what's important to note here, even though 360 compared to 5.7 doesn't seem like that big of a difference, it is a humongous difference in terms of the number of microstates these molecules can occupy. So the trend that we see here is with increasing complexity of our molecules will come increasing microstates or increasing entropy. And so we can see that more quantitatively on this phase diagram right here. Okay, so we remember a good formula for delta S is delta H divided by T. And as we look at the entropy of our materials, right, starting from negative 273 Celsius, which would be 0 Kelvin, right, we would be starting at 0 entropy. This is an example of water right here. So this is all H2O. So you can see entropy increases steadily as we increase the temperature of that solid, which makes good sense because now it's free to like vibrate and kind of move around a little bit. And then we hit 0 degrees, and now all of a sudden we see a huge jump in entropy. Okay, so that huge jump is related to the fact that a phase transition is occurring. And what we get from that is this delta S of the phase transition. And of course, that delta S of the phase transition is really related to the delta H of the phase transition divided by the temperature at which it happens, okay? So, and you can also see there's not a whole lot of difference between a solid and a liquid, but now when we look at the difference between a liquid and a gas, there's an enormous delta S of vaporization. That's because liquids and gases are very different in terms of how many microstates they can occupy and how much entropy they have, okay? And of course, like I said, we talked about this already, but if we were now to look at the same molecule, or rather the same temperature, but now we change the molecular structure, we can see as we increase the number of carbon atoms in this chemical structure, we're getting an increase in entropy, which is to be expected. Okay. So let's see. So we're going to move on now into calculating entropy for a chemical reaction in the next video.